Welcome to the amazing world of calculus made simple. In this video, we're going to talk about the derivative and the tangent line problem, one of the beginnings of calculus. All right, so let's talk about what's called instantaneous rate of change. The slope, rate of change, at one specific point, x equals a on a function. That is what instantaneous rate of change is. It's not the rate of change between 2 points, it's the rate of change at a specific point, a, on a function. I'm just using a to be super general. This instantaneous rate of change can be found by analyzing the slope of the tangent line at this point, a comma f of a. Now, please make sure you understand, of course, a would be my x value, f of a would be the corresponding y value. I'm just staying generic by using a and f of a. But how do we define the tangent line at a point? Again, how do we define the tangent line at a point? Well, for a circle, the definition of a tangent line at a point P is the line that is perpendicular to the radial line at point P. So, of course, if we have a circle and we'd say, hey, I'm tangent at this point P, that's because if I draw a radius perpendicular to that line, we create the tangent line. It touches the circle one time. Okay, that's great, but what about a general curve, just any curve, right? Well, in this context, it becomes a little bit harder to define what a tangent line is. So we could say that the tangent line is a line that crosses the curve at one point, which would work in this picture. So right here we have my point right there, and of course I draw the tangent line. It crosses that blue curve at that one point. So that definition about crossing the curve at one point would work here, but it would not work in this picture. In this picture, we see that at the point P right here, we have our tangent line, but we notice it also crosses the curve over here. So I can't officially say that the tangent line is a line that crosses a curve at one point because that would actually not be true in this picture. So it's like in this general vicinity, yes, we cross the curve at one point, or we touch the curve at one point. But if we kind of zoom out and look at the entire function, we cross more. And actually, if we consider that this end of the curve continues to go up, we actually are going to cross a second or a third time, actually. So I don't know if that definition really works either. So this is actually the problem. This is the tangent line problem. It's like, how do we define what the tangent line to a function is? So instead of focusing on defining that, we actually focus on finding the slope of the tangent line at point P. So instead of focusing like on what is the definition and all that kind of funky stuff, we say, all right, let's worry more about not how to define what that tangent line is or what that tangent line is. Let's focus on finding the slope at a point P on a function. All right, so we're going to do that with something that we call a secant line. So we start off by considering the slope of the secant line. Now let me break down what's going on. First, let's talk about slope. Everybody should know what slope is. Slope is change of y over change of x. Now, if you've never seen that triangle symbol before, that is the Greek letter delta. And mathematically, the Greek letter delta means change. So this literally means the change of y on top divided by the change of x. Now, you guys probably know that more as subtracting the y's and then subtracting the x's. So, of course, that is our formula for slope. But if we want to be a little bit more advanced calculus level here, we use that delta symbol. Now, what I'm going to do is find the slope of the secant line. Now, remember, a secant line crosses your curve twice, not once like the tangent line. So if I'm trying to find the slope at this point right here, P, this beautiful, amazing red point right here. So I start off by using that point. Obviously, that point would be a comma f of a. Again, staying super generic. A is any number, 2, 3, 5, negative 6. And then f of a is what happens when you plug that number into the function. So it's, again, it's my input, my output, my x and my y. But now we need a second point. So here, I'll use green right here for my second point. And that second point is simply h units away. So if here is my first x value, if I slide over h units, I have my second x value. So you could look at h as my change of x, right? So that would be right here. H would be how much I changed my x. So my new point would be whatever the original a value was plus h. It's just, moving it over h. And then my y value would be f of whatever that value is, a plus h. So just to kind of, I want to stay very generic here, but just to be a little bit more specific, if my first point was 2, 5, then if I decide, hey, I'm going to move over 6 units, then my next point would be 8, well, whatever f of 8 would be. I'd have to plug it into the function to find out. But again, that's my change of x. That's my h, how much we changed. In this case, it'd be 6. So again, that is how you find the slope of a secant line. You have one point, a, f of a. You have a second point, h units over. That's my change in x. And that second point is a plus h, f of a plus h. And again, how do you find slope? Well, change of x over change of y. Oh, whoa, I can't believe I said that. A big sin right there. Change of y over change of x. So my numerator is going to be my second y value, f of a plus h, minus my first y value, f of a, and then my denominator is going to be my second x value, a plus h, minus my first x value, f of a. And some people, some upper level calculus books, they don't like using h. They'll use the delta x. Again, that's delta x could be just your change of x. Delta x and h are, again, essentially the exact same, not essentially, they are the exact same thing, just two different ways of looking at it. If you just want to look at it as a number, you'd call it h. If you want to look at it more holistically, we'd say it's the change of x. So I could also replace my h with delta x, which is just how much I'm changing my a value by. No big deal. All right, now the cool thing is in the denominator, the a's cancel because really the a plus delta x minus a, the a's are going to reduce to a 0 because that makes sense that your denominator is simply your change of x anyway. And if I'm going from a to a plus h, my change is just that h or again that delta x. So here at the very bottom is our final formula for the slope of a secant line. Again, it's really not that complicated. It's probably spending way too much time on it. I'm just taking my y values on top, subtracting them, dividing it by subtracting my x values, but the subtraction of your x values is what we literally just call delta x, the change of your x. All right, so this formula is called the difference quotient. Big vocab word there. It is a really simple, very common sense formula, and the denominator represents the change in x, hence delta x. The numerator is the change in y, hence the delta y. Pretty simple. Overall, not too bad. Now, here's where it gets spicy. We could obtain more and more accurate approximations of the slope of the tangent line by choosing a point closer and closer to the point of tangency. So again, remember, we're starting off by trying to find the slope of the tangent line, but we actually just introduced you to the slope of the secant line. But here's the idea. If this is the point that I'm trying to find the tangent line at, this is the point I'm trying to find the slope of the tangent line. Here it is again. Well, if I take my second point right here and I slowly move it closer, notice as I move it closer and then even closer, the line that is the secant line, because the secant line is crossing twice, but that line gets closer and closer to the tangent line. So if I allow the distance between my 2 points to get closer to 0, the better the approximation will be. As the change in x gets closer to 0, the better the approximation is. And again, the change in x is the same thing as saying the distance between the 2 points. So if I allow that distance to shrink, again, that's that horizontal distance. Here it is right here. If I allow my change of x to shrink, there it is. You can literally see it shrinking over here. It's so tiny, I could barely fit it in there. If you allow that change of x to shrink, the slope of the secant line gradually gets closer to the slope of the tangent line. Now, this is exactly where we could now introduce limits, because the idea of something getting closer and closer and closer and closer and closer to 0 is the concept of using a limit. So now we can actually formally define the tangent line with slope m. So this is the definition of the tangent line with slope m. If f of x is a function, and it is defined on an open interval, I guess it should be defined, sorry about the typo there. It's defined on an open interval containing a, and if the limit exists, now listen here, I wrote it twice. I just use, again, delta x is the same thing as h. Just change of x is the same thing as h. The slope of the tangent line is the limit as the change in x approaches 0 or as h approaches 0, same thing. And again, I'm using the slope of the secant line. But as that secant line change of x gets closer to 0, I get closer to the slope of the tangent line. So again, if I just add the limit in front of my difference quotient, I get a formula not to find the secant slope anymore, but to find the slope of the tangent line. Okay, let's back that up one more time. Here is how I found the slope of the secant line. It's simply slope between 2 points. We call that formula the difference quotient. But if we allow the denominator, the change of x, to slowly get smaller and smaller and smaller, closer and closer to 0, the slope of that secant line gradually turns into the slope of the tangent line, which is what we're trying to find in this video. So using a limit is how we allow that change of x, or we want to call it h, to get closer and closer to 0. So this is the definition, the formula to help us find and understand the definition of a tangent line. So we can't define the tangent line using like, well, it's when you cross a function once, or if you touch a circle once, or listen, this is how we define the slope of a tangent line. It makes much more sense, and it doesn't matter if it crosses the function somewhere else. It's about being the slope at one specific point. Okay, so now what I want to do is, well, like put this to use. Like let's actually use this formula to find some tangent line slopes. All right, so here we go. We're going to do a couple different problems here. They range in difficulty. So really, let's take our time here showing all of our work. I'm going to show all my work. I recommend you do too. And the algebra can get a little bit weird, a little bit funky. So hopefully you're good at algebra, because that's going to hold you back if you're not. All right, so let's find the slope of the graph 2x minus 3 at the point 2, 1. Okay, so essentially 2 is my a value and 1 is my f of a. All right, so now I'm just going to use the formula. So the slope of the tangent line is the limit as h approaches 0 of f of, okay, now I'm no longer using a because I actually have an a value, 2 plus h minus f of 2, that's my f of a, all divided by h. Again, I'm literally using the formula. Let me go back to it real quick. All I'm doing is now I have a specific problem where a is 2. All right, now, how do you solve a limit? Well, you can always try direct substitution. If I actually plug in 0 right now for h, I get f of 2 minus f of 2, that's 0, divided by 0. Okay, so if I plug in h right now, I get 0 over 0, and that is bad. But that actually means the limit does exist. I just have to do some algebra work to find it. So here comes all that fun algebra work. All right, let me continue on here. What is the limit as h approaches 0? All right, first off, I'm actually going to take the 2 plus h, and I'm going to plug it into the function. So the function is 2 times 2 plus h minus 3. I literally took 2 plus h and plugged it into the function. That's what function notation means. Minus, now I have to take 2 and plug it into the function as well. Oh, I've already done that. It's 1. I already know the answer to that. Now, you could double check if you want. 2 times 2 is 4. 4 minus 3 is 1. But I already knew that f of 2 was 1. All divided by h. Okay, I guess I could try to plug in 0 now. Again, always try direct substitution. But if I plug in 0 for h right now, here and here, I'm going to get 4 minus 3 minus 1. That's still 0. And I still get a 0 in the denominator. So that's not going to work. I got to do some more algebra. All right, so now I'm just going to do a little bit of just algebraic cleanup work. Distribute the 2. So I get 4 plus 2h minus 3 minus 1, all divided by h. I'm going to keep going with some good old-fashioned algebra work. Now, I'm going nice and slow here on purpose. I have 2h. Now, let's see here. 4 minus 3 minus 1 are all like terms. 4 minus 3 minus 1 is 0, so that's gone. So don't even have to write it. All divided by h. No, oh my gosh, oh my gosh, oh my gosh. My h's are going to reduce. H divided by h is 1. So at this point, I get the limit as h approaches 0 of 2. All right, now let's try plugging in 0 for h. Again, always try direct substitution. Well, there's no h to plug in. It's a constant, and the limit of a constant is that constant. So there's my final answer, 2. This is so easy, so simple. Hopefully you followed all of my work. Now, let's actually back up for a second. This should actually, if any problem, this should make the most sense. This is a linear function. And there's one thing you should already know about linear functions. They have a rate of change that is constant. So if the slope of this linear line is 2, which we all know just by looking at the linear line, 2x minus 3, we know the slope is 2, then that should mean at any point on that line, the slope is 2. So no wonder I got an answer of 2. Nice and simple. All right, let's try another one. This one's a quadratic, going to be a little bit different. All right, so once again, we want to find the slope of the graph for the function negative 2x squared plus 5 at x equals 3. Now this time they gave me my a value, but they did not give me my f of a value. But listen, I could find that, just a matter of just plugging it in. So let me just do that work real quick. 3 squared is 9. Negative 2 times 9 is negative 18. Negative 18 plus 5 is negative 13. So there's my f of a value. Just plugged 3 in. All right, so now I want to find the slope of the tangent line at 3. So I'm just going to use my formula. The limit as h approaches 0, and I'm going to just plug in 3 for a, so it's going to be 3 plus h minus f of 3, all divided by h. And now I'm, again, same thing I did in the last problem, I'm literally going to take 3 plus h and 3, and I'm going to plug them into my function. That's what function notation means. So I have the limit as h approaches 0. Let's see, you're plugging 3 plus h in, that's going to be negative 2. Times 3 plus h squared plus 5 minus, well, I already know what happens when you plug 3 in. Again, I've already done it. We get a negative 13 when we plug 3 into the function, all divided by h. Now, once again, you could try direct substitution right now, plugging in a 0 for h and h, but you're going to get a 0 divided by 0. Now, that means that the limit does exist. I just have to keep going and try to find it. All right, so this is where my good old-fashioned algebra work is going to come in handy. Okay, so now I need to literally square out order of operations. I got to do 3 plus h squared first. So I have negative 2 times 9 plus 6h plus h squared. Hopefully you're following my algebra there. Plus 5 plus 13. 2 negatives do make a positive right there. Oh, divided by h. I'm going to keep going. The limit as h approaches 0. Now I'm going to distribute that negative 2. Negative 18 minus 12h minus 2h squared plus 5 plus 13, all divided by h. And I'm going to keep going with my algebra, doing some combining of like terms here. So let's see, I got a 5 and a 13. That's 18 right here. I already have a negative 18, so that's going to make a 0. So that's all gone. And then I have a negative 12h minus 2h squared, all divided by h. All right, so now I could try plugging in 0 again for the h values here, here, and here, but I'm still going to get 0 over 0. So I got to keep going with my algebra. And let's see here. I'm going to factor out an h on top. I'll be left with negative 12 minus 2h if I factor out an h. Oh, this is awesome. Now these h's are going to reduce, and h divided by h is a 1. And now I have the limit as h approaches 0 of negative 12 minus 2h. Okay, now let's try direct substitution. Let's actually plug 0 in for h. I get negative 12 minus 2 times 0. And that does not yield 0 over 0. That yields a negative 12. So there's my final answer. On this function, at an x value of 3, more specifically at the point 3 comma negative 13, the slope of the tangent line is negative 12. Lots of good, fun math work there. I think it's fun, maybe you don't. But notice what happened in the last two problems. I wasn't done until I get the h in the denominator to cancel. keep that in mind. When you are using this formula, your goal should be to get that h in that denominator to cancel. That's when you could plug 0 in for h and no longer get the double 0. All right, let's try another one. Now, this one's going to have a lot of really good algebra, trust me. So we want to find the slope on the graph of x plus 2 over 2x minus 5 at the point 1, comma, negative 1. All right, so once again, I'm going to find the slope of the tangent line. I'm going to do a limit as x, or not x, sorry, h approaches 0. And I'm going to plug 1 in for a, so that's 1 plus h minus f of 1 all divided by h. All right, now I'm going to actually go ahead and plug in 1 plus h into my function. So I get 1 plus h plus 2 all over 2 times 1 plus h minus 5 minus f of 1. And that again, that I already know that. That's negative 1. But I could plug in 1 if you want to check the work. 1 plus 2 is a 3 on top. 2 times 1 is 2. 2 minus 5 is negative 3. 3 divided by negative 3 is a negative 1. So I get minus that value of negative 1, all divided by h. All right, let me continue to use some algebra skills to clean this up here. So in my numerator, if I combine like terms, I have an h plus 3. In my denominator, if I distribute the 2 and then combine like terms, I'm going to get a 2h. The 2 and then minus 5 makes a minus 3. Plus 1, all divided by h. All right, so once again, maybe I could try right now by plugging in a 0 for the h's, and I'm going to get a 0 on top and a 0 on the bottom, so that's obviously not going to work. So I got to do some more advanced algebra here. Again, the key is to get this h in the denominator to cancel out. So let's keep going with some algebra work. All right, the limit as h approaches 0. Let's actually add the numerator together. Let's actually get one fraction in that numerator. So I have h plus 3 over 2h minus 3. I'm going to turn the 1 into 2h minus 3 over 2h minus 3. That way I have a common denominator. Again, all I did was get a common denominator on top, all divided by h. I'm going to keep going here. The limit as h approaches 0. Okay, now I'm going to actually add my numerator together. So let's see, combining like terms in my numerators, now that I have a common denominator, is going to be a 3h. Oh, that's it, right? The 3 and the negative 3 are going to reduce to a 0. My common denominator is 2h minus 3. Now I'm going to do one step next that a lot of kids, if you're not good at algebra, are going to get a little bit confused by. But instead of dividing it all by h, I'm going to multiply by the reciprocal. Well, what's the reciprocal of h? 1 over h. So again, instead of dividing everything by h, I just multiplied by the reciprocal, 1 over h. Now, this is actually awesome because check out what's about to happen. This is what I've been waiting to happen. This h and this h will cancel because they're common factors. H divided by h is 1. So I get the limit as h approaches 0. I have just a 3 on top and a 2h minus 3 in the denominator. All right, now that I got this h right here to cancel, there it was right there, I got it to cancel. Now I'm going to plug 0 in for h. I get 3, again, that's called direct substitution. That's how you can solve limits. So I get 2 times 0 minus 3. That's going to be 3 divided by negative 3. 3 divided by negative 3 is negative 1. So, on this function right here, there is a point. The slope of the tangent line at that point is negative 1. There it is. I did it. So awesome. All right, let's dive into a second problem. Oh, actually, this is the fourth problem. This is a really good one involving square roots. It's going to involve some really good algebra skills. So we're going to dive right into using the formula. The slope of the tangent line is the limit as h approaches 0 of f of, and I'm going to replace it with 8 plus h minus f of 8 all divided by h. Now, once again, 8 is my a value, my corresponding y value, or f of 8 I can find. Actually, it's really simple, radical 3. 8 minus 5 is 3, square root of 3 is square root of 3. Unfortunately, it's not a perfect 9 or 16, but you know what? Life goes on. All right, so now I just got to, again, I got to do something to get this h in the denominator to cancel. That is always my end goal. All right, so first here, I'm going to go ahead and actually plug 8 plus h into the function. Square root of 8 plus h minus 5 minus f of 8. We can already know what f of 8 is. That's radical 3. All divided by h. And again, try to plug 0 in for h. Try direct substitution right now, but you're going to get a 0 over 0. And that's what tells me I got to keep going. I got to keep going here. All right, so what is the limit as h approaches 0? So let's see here. What can I possibly do? Okay. This is a pretty advanced algebra technique. So pay attention. You're only going to ever use this technique when you're working with square roots. We're going to multiply by the conjugate. The conjugate is the square root of 8 plus h minus 5 plus the square root of 3. Now, in a moment, you're going to see why multiplying by the conjugate is so awesome. But I can't just multiply the numerator because that actually changes it unless I also multiply the denominator. So essentially, I'm multiplying by 1. Now, a really weird way of looking at 1, but anytime your numerator and denominator match up, it's 1. So I'm multiplying both the top and the bottom by the conjugate. Now, let's start with the bottom. Let's start at the bottom. The bottom is just pretty boring. It's going to be h, that's this h right here that I'm trying to get to cancel, times the square root of 8 plus h minus 5 plus the square root of 3. Now, actually, I should be honest here. This could be changed to the square root of h plus 3 because 8 minus 5 is 3. And same thing here. I'm actually going to go ahead and do that. That's the smart thing to do just to make it, I don't want to say easier, but make it, simpler to write. These problems do involve a lot of writing, so anytime the writing can be shorter, I'm going to obviously like to do it. So it's going to be h plus 3. All I do is combine the like terms of 8 and minus 5. And again, h plus 3. Okay, so across the denominator, I have h times the square root of h plus 3 plus radical 3. Okay, now, the numerator is where it's going to get really fun. Because when you multiply conjugates, the inside and outside terms always cancel. I have a binomial times a binomial. So I'm going to multiply the first parts together. Square root of h plus 3 times the square root of h plus 3 is just h plus 3. The square root goes away because when the square roots are both exactly the same, they multiply and you just get the inside. Now, the last part is multiplying the negative radical 3 times positive radical 3, and that's just going to be negative 3. It's actually going to be negative square root of 9, but negative square root of 9 is 3, negative 3. Okay, now what about the inside and outside terms? They canceled. Notice that the outside terms and the inside terms are both exactly the same, one positive, one negative. They're going to reduce to a 0, so why even bother writing them down? This, again, is the whole reason why I use the conjugates. All right, now continuing my work here, the first thing I notice that these these 3's are going to cancel, which is awesome. So I have the limit as h approaches 0 of h all divided by h times the square root of h plus 3 plus the square root of 3. Now again, here it is. This is what I've been waiting for. These h's are going to reduce to a 1. H divided by h is 1. That is what I've been waiting for. Again, all of the good algebra is to simply get me to this point. The limit as h approaches 0 of 1, that's the h divided by h, divided by the square root of x, not x, it's an h, plus 3, plus the square root of 3. All right, now that I got that h to cancel, we can actually go ahead and use direct substitution. Plug 0 in for h. I get 1 over the square root of 3 plus the square root of 3. Again, if I plug in a 0 for h, 0 plus 3 is 3, square root of 3 plus square root of 3. Now, please, the square root of 3 plus square root of 3 is not the square root of 9. It's not the square root of 6. It is 2 radical 3. Radical 3 plus radical 3 is 2 radical 3. 1 apple plus 1 apple is 2 apples, so 2 radical 3. So there is my final answer right there. What is the slope of this function at 8? There it is. That's the slope of the tangent line at that point. Okay, pretty cool, pretty simple, not too bad. That's it for part 1. Please stay tuned for part 2 of the derivative and the tangent line problem. But what we just accomplished was how to first define what the tangent line is based on its slope. Pretty cool. Hopefully you understand all of my work there. Go back and watch again if you need to. And then we actually put this formula to work to find the slope of a tangent line at given points on a function. All right, stay tuned for part 2. It's going to be a great one.